Let's suppose that we're going to mix up some salt solution in a big mixing tank. So suppose we start out with a 100-liter mixing tank that starts with pure water. And into this we pump a salt solution at 5 liters per minute. And that salt solution has some salt in it that's 20 grams of salt dissolved in each liter of water. As we pump this salt solution in, we don't want our tank to overflow, so we also pump mixed solution out at the same rate, 5 liters per minute. So how long will it take for the resulting mixture to reach half of its ultimate value? So I guess first we're going to have to come up with some function that tells us the concentration as a function of time, and then we're going to have to figure out, well, what is its ultimate value, and then how long does it take to reach half of that? So first let's just see if we can figure out some way of describing how much salt is in the tank. It's not really clear at first whether so we might use maybe C of t for concentration at time t. Or, maybe it would be easier to use just the amount of salt at time t. I think I'm going to use the amount of salt instead of the concentration, but since our tank has a constant 100 liters of liquid in it, the concentration will just be the amount of salt divided by 100. So we can switch between these two at will. But for my own reasons, I'm going to use the amount of salt as our unknown function here. So we know how the amount of salt is changing because we know how we're pumping fluid in, and we know how we're pumping fluid out. And that's what causes the change in the amount of salt. So probably what we should think about is not the function s of t directly, but instead we should probably think about its rate of change. So what is causing change? Well, change for the amount of salt in the tank. Well, there's an increase in the amount of salt because stuff is flowing in, but then there's a decrease in the amount of salt in the tank because there is this solution flowing out. So what is the flow in? Well, the flow in, it has concentration 20 grams per liter, but if you look at the units for this derivative, right, this amount of salt, when I say amount, I guess what I really mean is mass, and so this should be in grams. So S is in grams, and time is in minutes, it looks like. So when we express the flow of salt into the tank, it ought to be in grams per minute. Well, if we write down the flow rate of fluid coming into the tank, it isn't in grams per minute, it's in liters per minute. So we need to do something to make this 5 liters per minute of fluid flowing into the tank. We need to do something to make this into the number of grams of salt per minute that flow into the tank. But if you look at the units for this concentration here, you'll see if we just multiply this concentration by the flow rate, so 20 grams per liter times the flow rate, then the liters cancel, and we do get grams per minute. So there are 5 times 20, that's 100 grams per minute of salt flowing into the tank. Okay, so the idea here was we had the flow rate times the concentration. And these are both in, the flow rate in times the concentration in. That gives us the rate of salt flowing into the tank. But we can do the same thing for the flow rate out. We can just for the flow rate of salt leaving the tank, we can do the flow rate of fluid going out times the concentration of the solution that's going out. So the flow rate out is still 5 liters per minute. Right, that's right here. We don't want our tank to overflow or empty out, so we pump out at the same rate we pump in. But what is the concentration of that stuff leaving the tank? Well, the only thing we know about the salt in the, about the fluid leaving the tank is that it's well mixed. So what does that mean exactly? Well, I guess that means that the concentration in everywhere in the tank is equal, right? There's not one part of the tank that has more salt in it than another part. So if the concentration is uniform throughout the tank, then we can find the concentration just by taking the amount of salt in the tank and dividing by the volume in the tank. So concentration is mass of salt in the tank in grams divided by the volume in the tank in liters. And the volume of the tank is 100 liters. And what is the mass of the salt in the tank? Well, that's S of T, right? That's the unknown function that we don't know yet. So I'll just write S. And this is in grams. And if we look at the units, everything is working out. So these liters simplify away, and we're getting grams per minute. So everything on the right-hand side is in grams per minute, which is what it's supposed to be. So that's a good sign. Now that all the units work, now that we know all the units work out, we can do our calculation without writing all the units, and then just put the units back in at the end. So this is ds dt equals, so 5 times 20 is 100 minus, so 5s over 100, that's s over 20. Okay, so we get this differential equation. We'd like to solve this differential equation one way or another. Fortunately, because t doesn't show up on the right-hand side of this equation is automatically separable. So we can separate in the usual way. I guess we could start out by, let's see, what would be the best way to do it? Let's just divide both sides by 100 minus s over 20, I guess. Same thing on the right-hand side. So we get 1 over 100 minus s over 20 equals dt. Oops, I missed my ds on the left-hand side. While we're at it, why don't we multiply both sides by minus 1 over 20. So on the left-hand side, I'm doing this really just to make this denominator a little nicer. So on the left-hand side, the fact that we're multiplying by a negative switches these two terms around, and because of the 20 in the denominator, we get s minus 2,000. And then on the right-hand side, minus 1 over 20 dt. And I missed my ds again. All right, now we can integrate on both sides. On the left-hand side, we get natural log absolute value, s minus 2,000. On the right-hand side, minus 1 over 20 times t, plus a constant, right? Can't forget about your constant of integration. And then exponentiate, so absolute value of s minus 2,000 equals e to the minus 1 over 20t times e to the c, which I'm going to call a. So a is e to the c. And a has to be positive because it's e to the c, right? E to the c is always positive. But then when we remove these absolute values, that has the effect of putting a plus or minus on the right-hand side. So it's really plus or minus a. But if a is positive, plus or minus a can be positive or negative. And so why don't we just say that a is anything rather than strictly positive. So a times e to the minus 1 over 20 times t. And finally, we can finish solving for our unknown function s. It's a e to the minus 1 over 20t plus 2,000. All right. Now remember, so this is all solutions to the differential equation. It turns out that this is a general solution. But remember, we want a particular solution because we had an initial value. The initial amount of salt in the tank was 0 because it started out being full of pure water. So if we put in 0 for time, we should get 0 grams of salt. But we can plug t equals 0 into the formula that we got. So we got a times e to the 0 plus 2,000. And then we can solve this for A. A is minus 2,000. So S of t is minus 2,000 e to the minus 1 over 20t plus 2,000. Or if you want, you could factor out that 2,000. So 2,000 times 1 minus e to the minus 1 over 20t. Okay. Now remember what we were going to do with this. We wanted to find out how long it takes until the concentration is half of its ultimate value. But the concentration, right, we said concentration is just the amount of salt divided by 100. So that's going to be 20 1 minus e to the minus 1 over 20t. We want to know when we get to half of the ultimate value, but what do we mean by ultimate value? I guess that means the long-term value that this concentration goes to, but that's really just a limit. So the ultimate value of the concentration is the limit as t goes to infinity of c of t. And if you look at this formula, since t only shows up in this one spot, we just have to ask ourselves what happens when this exponent, when this t in the exponent gets really big. Well, when the t in the exponent gets big, we get e to a large negative, that is 0. So in the limit, this exponential part becomes 0, and we just get 20. So the ultimate long-term value of the concentration is 20 grams per liter. And so half of that is 10. So we need to know that to find when the concentration gets to half of its ultimate value, we can just set c of t equal to 10. And c of t is 20 times 1 minus e to the 1 over 20 minus 1 over 20t, and then solve. So 1/2 is 1 minus e to the minus 1 over 20t. So e to the minus 1 over 20t is equal to 1/2. And then take natural logs. Minus 1 over 20t is natural log of 1/2. And so t is minus 20 times natural log of 1/2. And that is, so minus 20 times natural log of 1/2. 13.86. And this is minutes, since our time units were minutes at the very beginning. So it takes almost 14 minutes for the concentration of the salt water in the tank to reach half of its ultimate final value.